Hello everyone, you're welcome to Meshed Up Mentors. This is Python for All series, PY4A. Kindly subscribe to my YouTube channel. In this video, I want to discuss students' t-test and analysis of variance, also known as ANOVA. First, let's start with the t-test. A t-test is an inferential statistic used to determine if there's a significant difference between the means of two groups and how they are related. For comparing two independent samples, we have the t-value defined by the mathematical expression below. For one sample test, the t-value is defined by this mathematical expression. So to conduct our t-test and ANOVA analysis, we will need the following libraries. We will need the NumPy, the Matplotlib, the Seaborn to access some data. Also from SciPy, import stats, which is a statistical package or library in SciPy. Import Pandas as PD. Then we need this library Statsmodels.api. I will import it at SM. Then from startmodel.formula.api, I import OLS. OLS is the ordinary least square regression, which I will use to regress my data. Having imported all these libraries, so next is to generate my data to compute the one sample t-test. So here I have used a random seed so that each time I run this cell, I get the same set of data generated for me. So the number of data points is 31, the population mean is 60, and then my degree of freedom is 30, which is number of samples minus 1. So I will call my student score to be np.random.runInt. I want random integers between 20 and 100 in the total number of the degree of freedom, which is 30. Running this gives me my student score. If you print to have 30 student score. So next is for me to compute the t-stat and the p-value. So I will use the library or the package that I've imported from SciPy, which is stats. So I'll call start.t-test underscore one samp, and I'll pass in the student score. The population mean is equal to mu. If we run this and print the result, what do we have? We have t statistics equals 0.191, and then we have the p-value equals 0.85. What's the interpretation of this? The p-value is a statistical measurement to validate a hypothesis against observed data. Typically, the threshold value is 5% or 0.05. And what does that imply? It implies that if any p-value is less than that threshold, we should reject the null hypothesis, implying that there is a significant difference between the sample mean and the hypothesized population mean. Else, in other words, if the p-value is greater than alpha, we should accept the null hypothesis, implying that there is no significance in the difference between the sample mean and the hypothesized population mean. So based on our result, if you run this condition, what do we have? We should accept the null hypothesis, implying that there is no significant difference between our sample mean, okay, and the hypothesized population mean. The next I want to conduct is the t-test for two independent samples. The first one we have looked at is just for one sample. Now we want to look at two independent samples. So I will import the iris data set from the Seaborn library. So we have Seaborn library imported as SNS dot load dataset. I will load iris dataset. And then we can see the content of our iris dataset. We have four properties there. We have the column for the sepal length, the sepal width, the petal length, the petal width of the species Setosa and Virginica. And so I would take a DF of Setosa to be equal to Irish Setosa, where Irish Setosa DF of species is equal to Setosa. I will do the same thing for Virginica. So that I will have these two data frame in my namespace. T-stat and p-value, okay, being equal to start.t-test. Because we are doing for two independent values, the t-test will be underscore ind, which is end. And then you pass in your samples. Okay, so the sample points are df setusa dot petal length against Virginica petal length. So running this will return t statistics and the p value. The t statistics is negative 49. There's not too much significance of in terms of interpreting the t statistics, other than the fact that it tells you the deviation between the mean and the standard deviation. Our focus specifically is on the p value, okay, which helps us to either accept the null hypothesis or to reject the null hypothesis based on the result that we have. So we can see our p-value here. And so we also pass in the threshold again and then pass in the conditional statement. If p-value is less than alpha, we should reject the null hypothesis, which is the alternative hypothesis. Else, we should accept the null hypothesis. So running these, what happens gives us the result that we should reject the null hypothesis because our p-value is way less than 0.05. And what is the meaning of that? It means that there is significant difference between the sample petal length of Iris setosa and Iris virginica. Another thing I can do here is to look at the distribution, the histogram distribution of the Setosa petal length and the Setosa, the Virginica petal length. So I've done that here by calling df Setosa dot petal length dot histogram and colored red. Let me change the color to orange. I love orange. And then df Virginica dot petal length dot histogram color green. So this is the histogram distribution for DF Setosa petal length, and then for Virginica petal length, this is the distribution that we have. The next we're going to look at is analysis of variance, ANOVA. Analysis of variance simply compares variance between group means to variance within group means. If the variance between group means is larger than the within group, it suggests that there are differences in means among the groups. Now we have two type of ANOVA analysis. We have the one-way ANOVA analysis. Here there is one independent variable and two or more groups, or what you can call category or levels. The other is the two-way analysis of variance. Here there are two independent variables, and each variable has two or more groups or levels or categories. And before we start our ANOVA analysis, we have to, first of all, state our ANOVA hypothesis. The first is the null hypothesis. And what is the null hypothesis saying here? That group means are equal, meaning that there is no variation in the means of the groups. Mathematically, it is stated as H naught, the null hypothesis, mu1 equals mu2 equals mu3 equals mu until mu p. We also have the alternative hypothesis. Here, at least one group means is different from the other group. By that, we have mathematically H1 stating that all mu are not equal. Let's proceed by demonstrating these two analysis of variance, the one-way and the two-way ANOVA, and also testing our null and alternative hypothesis. Let's go straight to the one-way ANOVA. Here, I will import my data, diffcycle.csv, from my own directory. I have it here down in messed up mentors in data. I have diffcycle.csv. Right? I will leave a link to the download of this data in the description of this video. So load it with pandas.read.csv and then display the data frame or print data frame. You can see we have a 3-column person, dose, and libido. The dose has of 3 levels, 3 categories. We have the 1, 2, and 3. So we are going to categorize the dose and see how each level of dose affects libido. That's exactly what we want to. But because the analysis does not involve the persons, what I will do is to drop that column person and focus on the two columns, the dose and the libido. So I'll come here and do df of drop person, axis equal to 1, in place equals true. Then if you run df.head, we can see that we have dose and libido in our data frame. The in place actually helps us to perform the action in place instead of modifying the data frame and assigning it to another data frame. I just modify that in place. The next, I can use the box plot to see how the libido varies when grouped according to the dose. So we'll call df.boxplots libido group by, we're grouping by dose, and then plt.show. That returns this plot. Next is that because we have three categories, okay, represented by one placebo, two low, and three high in terms of the dose, I will call df.dose and replace those values with the categories. So I'll have one being replaced with, so one becomes the key. The values I'm replacing them with are the values in the dictionary here. So I have one placebo, two low, and three high, and the action should be done in place. If we run this and print, never mind this one telling us some feature changes in Pandas replace method. So if we look into our DF, we can see the dosage and the libido, placebo and libido. You can see them displayed here. I'm going to model my data. Now I'll call the OLS that I've imported from Statsmodel, okay, which is the statistical package. If you don't have it, just do pip install Statsmodels and it will install Statsmodels. I've imported from Statsmodels.api at SM and also from Statsmodels.formula.api OLS, the ordinary least square regression. So I want to regress my data. So to do that, the dependent variable is the libido. And I'll use the tilde symbol to point to the independent variable, which is the dose. But because the dose is a category, append a C before the dose and put the dose in brackets, comma, and then you pass in the data to be equals to the DF and call a fit on my model. Then the next thing is for me to compute the ANOVA table. Since I'm doing a one-way analysis of variance, I'll call sm.start.anova_lm, passing the model and the type equals 1. And afterwards, I'll print the ANOVA table. If under our DF, this value tells us the coefficient of the dependency of libido on dosage. And then we'll go through and look at our F statistics. And our focus is on the probability values, which is the P values. Here it is 0.02. This specifically means that this value, if less than our threshold value, meaning that we should do what? Reject the null hypothesis. Also, instead of using the OLS model, I can likewise use the stats package from SciPy to conduct the one-way analysis of variance. So I'll call fstats p-value equals stats dot f underscore one way. Now I'll pass in the respective columns. This might look a little bit clumsy here, but after this I would simplify this with a function and you see exactly what we're doing. What we're doing is we're getting a DF under the condition that DF of the dose equals high, okay, getting the corresponding value of that libido when it's high, comma, do the same thing for when it is low, do the same thing for when it is placebo. Okay, if we run this, what do we have? We have our F statistics to be equal to 5.11864. Exactly same result as the result we got from the OLS, ordinary least square regression model. And then the p-value 0.02, same result. Now, what we have done here can be put into a function. And I will define that function ANOVA one way. And here it will take a DF, features, and label. What are your features? Your features are simply the independent variable, while your label is the dependent variable. Okay, so I can actually come here and call it dependent variable, independent variable. Let's leave it as a feature. The label is simply the dependent variable. So I'll deep var, dependent variable. Okay, I'll put it in complete form, dependent, yeah, dependent variable, so that it be clear. So here, I'll come down here and first of all, get the unique features, the number of categories. There are three, placebo, high, and low. So I will call groups df of features dot unique, and it gives me three. So I will now have a list, okay, which I call group values, and then I will loop through the groups, and for every of those groups, I will get the df value corresponding to the dependent variable here, because I've changed this not label to the dependent variable. So that's exactly what I'm doing here is what was done here, but here is a little bit more readable. So after doing that, I will then run start.f1 way on unpack these group values by pre-appending this asterisk, and that will return the results. So let's run this function. Now I'll call analysis ANOVA one way, and here I will pass in my dependent variable to be libido. If we run this, what do we have? Returns the F statistics 5.111864, same result, and the p-value 0.0246. So you can see how I've used the statistic package from SciPy to do conduct one-way analysis of variance. Likewise, I've used the OLS from the stat model to also conduct the one-way analysis of variance. Next, we'll move to the two-way analysis of variance, the two-way ANOVA. And here I have a simple example, giving an illustration of a botanist who wanted to check whether or not plant growth is influenced by sunlight exposure and watering frequency. So she plants 30 seed and watched them for 2 months under those both conditions. And after 2 months, she has made a record of the height of the plant in millimeter. Now, we want to use two-way ANOVA analysis to determine if the watering frequency and the sunlight exposure have significant effect on the growth of the plant, and if also to determine if there's any interaction between the watering frequency and the sunlight exposure. So the next thing for do here is for me to generate my data. These are just fictitious data. So generating data have call a Pandas data frame on the dictionary with key water referring to the watering frequency. Here I have MP.repeat, okay, daily and weekly. I repeat that 15 times. Likewise, I have the sun, MP.tile, and then into MP.repeat, I have three levels, low, medium, and high. Repeat that 5 times, and then concatenate it down two columns. Actually, I have a video, okay, explaining this NumPy function repeat and tile, and I will leave it on the topmost right corner of this video. Follow that link, and then if you don't, you have a better understanding of what np.repeat and np.tie is doing here. And then lastly, I have the height with the values. Let's see the content of this DF. We have our water, sun, and height, both daily and weekly, and the three levels. Now, remember, in the sun is one of the dependent variables. Likewise, water is independent. Why the height depends on the sun or water or both interaction. And so we have three levels for the sunlight exposure. So let's go back to our model. We call model equal OLX. Now we put in quotation marks our height, which is the dependent variable, followed by a tilde symbol, water plus sun plus water asterisk sun. Now notice here that in both the water and the sun data, they are both categorical values, but I've not used C. Yes, in my previous example, I pre-appended a C to show that they are categorical values. You can actually do like that here. So you see that when you use a C or not, the OLS model from the start model, okay, understands this. And so that's why I've omitted that here. The asterisk here is to observe the interaction between the watering frequency and the sunlight exposure. So if we run these and then we have a model fitted, then we can then look at the result by calling the ANOVA table there sm.stats.anova_lm, passing the model we are fitted. I think I should call this model 2 and call this model 2. Let's rerun this again. Passing the model and what type. If you are doing a two-way analysis of variance, the type should be equal to 2. If we run this, we have our results. So this is the result from our table. You can see the DF giving us the coefficient of the respective independent variable, water, sun, and interaction between water and sunlight exposure. But our focus here is specifically on the p-values. So we can see the p-value for water, see the p-values for sun, and the p-value for the interaction between water and sun. What's the interpretation here? The p-values for water and sun are both less than 0.05. The threshold is usually 0.05. 5% is always usually the threshold. So both values are less than 0.05. Now, when both values are less than 0.05, what it simply implies is that both factors have a statistically significant effect on the plants. And for the second interpretation, the p-value for the interaction effect is 0.12, and that value is greater than 0.05. What that implies is that there is no significant effect between sunlight exposure and watering frequency interaction. So, what we have just explained here, I've put it down by passing them into this conditional statement, the if statement for the first and the if and else statement for the second interpretation. So, if we run it, it gives us the same interpretation that I explained earlier. With this, we have come to the end of this video. Like this video, share this video, and if you have not subscribed to my YouTube channel, please subscribe to my YouTube channel. I will leave a link of this notebook in the description box, as well as the diffsql.csv data file for download. I will see you in my next video. Bye.